Hey guys, today we're going to talk about mid-segments of a triangle. So we'll start with some vocab. A mid-segment of a triangle is a segment that connects midpoints of two sides of a triangle. That mid-segment is always parallel to the third side and half the length of the third side. So here's an example of what that can look like. So here's a triangle. Let's just say that right there is a midpoint. And this over here is a midpoint of this side. A mid-segment is a segment that connects those two. Okay? So let's just say this right here is x, then this would be half of x. So if this is 10, this is 5. If this is 12, this is 6. If this is 4, this is 8. Okay, so we're going to skip coordinate proof and go on to mid-segment theorem. The segment connecting the midpoints of two sides of a triangle, that's called a mid-segment, is parallel to the third side and half as long as that side. So DE here is a mid-segment. It is parallel to AC and it's half as long as AC. Alright, so this is supposed to represent a triangular window here with some segments. So we've got little partitions in the glass. In the diagram, DF and EF are mid-segments. So DF is a mid-segment opposite this side. EF is also a mid-segment opposite this side. Find the lengths of DF and AB. Okay, so DF, the blue mid-segment, is parallel to BC and half of its length. So DF has to be half the length of BC, so it's half of 90. So DF is 45 inches. Then find the length of AB, that's the side, the red longer side here. It's parallel to EF, and it has to be twice as long as that mid-segment. So AB is twice as long as FE, so it's 2 times 45, which is 90 inches. Okay, so I'd like you to pause the video and try to answer question 1. So in example 1, consider triangle ADF. Okay, so ADF is this triangle right here. What is the length of the mid-segment opposite DF? So the mid-segment opposite DF would be right in here, cutting AD in half and AF in half. Now this length right here is 45. So this right here is half of 45. And that is 22.5 inches. In the diagram at the right, QS is congruent to SP, and PT is congruent to TR. That makes ST a mid-segment. Show that QR is parallel to ST.
Go ahead and pass me to the main office. Thank you.
Because QS is equal to SP, and PT is equal to TR, S is the mid-segment of segment QP, and T is the midpoint of PR. Okay, so T right here is the midpoint of PR. Then ST is a midsegment. Got to go back here. That shouldn't have been a midsegment. That should have been a midpoint. Okay, so S is a midpoint and T is a midpoint, which makes ST a midsegment by definition of a midsegment. And a midsegment is always parallel its opposite side based on what we saw on page 1, the midsegment theorem. Okay, pause the video and try the checkpoint. So in example 2, if V is the midpoint of QR, what do you know about SV? Well, S and V are both midpoints, so SV must be a midsegment. So segment SV connects midpoints. So segment SV is a midsegment. Okay, so this part right here, we're not going to go very deeply into what this is all about. It's the coordinate proofs part that we skipped the definition of on page 1. This is just saying place a figure in a coordinate plane. When you do that, what this is trying to drive home is that if you're going to find the lengths of sides and midpoints and everything like that, it's really nice and easy if you use a vertex at an origin and place sides whenever you can along an axis. So this one is a square, so it says here it goes over S and up 0. S just represents any number. And this side goes over 0 and up S. So that gives a side length here of S and a side length here of S. Well, that just means this is over S and up S. So the coordinates are S, S. And then placing a triangle, 0, 0, and then go along an axis over, and it just says over B. It's just some made up variable representing a number over B and up 0. And this is over less than B, so we call it A, and up whatever number you want, so they called it H. We're going to go on to checkpoint 3. Place an obtuse scalene triangle in a coordinate plane that is convenient for finding side lengths and assign coordinates to each vertex. So 0, 0 is where we're going to start. Okay? Then over some amount, we'll just call it A, up 0. If it's going to be obtuse, I'm going to open this angle up this way so that it's bigger than 90 degrees and put a point up here. And that's over more than A, so call it B. And it's up more than 0, call it whatever letter you want. I'll call it L. Over B and up L. So there's my obtuse scalene triangle. All right, we're going to do number 1 on the front side of this page here. Determine whether the segment formed by points A and B is a midsegment. So A is at 5, 4. So here's A. B is at 3, 3. So here's B. Determine whether or not that is a midsegment. So here's one way we could do that. we could find the midpoint of MW and see if that is A, and then CW and see if that is B. So the midpoint of let's do CW first. So midpoint of segment CW. So for point C, the coordinates are 1, 5, over 1 and up 5. For W, 1, 2, 3, 4, 5, and up 1. Okay, so the midpoint is the sum of the x's over 2. It's 1 plus 5 over 2. And then the sum of the y's, 5 plus 1 over 2. So that's 6 over 2 and 6 over 2. 6 divided by 2 is 3, so that's 3, 3. Okay, so that tells me that B is a midpoint. Okay, then let's try the midpoint of MW. Okay, so point M is over 5 and up 1, 2, 3, 4, 5, 6. Okay, so the midpoint of MW, 5 plus 5 over 2, and then 6 plus 1 over 2. So that's 10 over 2 and 7 over 2, which is 5, 3.5. A is at 5, 4. That is not a midpoint. Since they're not both midpoints, I have to say that segment AB is not a midsegment. Okay, we're going to go on to number 4, which is on the back page here. Verify that SU is a midsegment. Okay, so I want to show that SU is a midsegment. In order to show it's a midsegment, we're going to do this in a different way. We are going to show that it's parallel to QR, and then we're going to show that it's half the length of QR. Okay, so for SU, the slope. Okay, slope is rise over run. See, S is at the coordinates over 3, up 3. And U is at 2, 0. Okay, so the slope is rise over run. That's the difference in the y's. 3 minus 0. So that's the y's. Over the difference in the x's, 3 minus 2. So that's 3 over 1. So the slope of SU is 3 over 1. Now let's find the slope of QR. 4 minus negative 2 is the difference in the y's. The x's is 6 minus 4. 4 minus negative 2, that's 4 plus 2, 6. 6 minus 4 is 2. 6 divided by 2 is 3, so that's 3 over 1. Same slope. So it is definitely parallel. Now we have to show that SU is half the length of QR. So we're going to use the distance formula. Distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, so in SU, the x's are 3 and 2, so 3 minus 2 squared plus the y's are 3 and 0, 3 minus 0 squared. 3 minus 2 is 1, squared is 1. 3 minus 0 is 3, squared is 9. So that's the square root of 10, and we'll leave it just like that. Then the distance for QR. In QR, the x's are 6 and 4. 6 minus 4 squared And the y's are 4 and negative 2, 4 minus negative 2 squared. So that is 2 squared, which is 4. And 4 minus negative 2 is 6 squared, which is 36, which is the square root of 40. And at first glance, it really doesn't look like this is exactly 2 times this. It kind of looks like it's 4 times this. But what we're going to do is simplify this radical. 40 is 4 times 10. 4 is 2 times 2, so there's a pair. 10 is 2 times 5, and that's as far as we can break that down. So there's a 2 that comes out, so that pair of 2's comes out as a 2. 2 times 5 stays in, which is 10. So it's 2 times the square root of 10. So the distance of SU is 10, square root of 10, and the distance of QR is 2 times the square root of 10. That's exactly double. Okay, so we have shown that the slopes are the same, and we've also shown that the length of SU is exactly half the length of QR. And since they're parallel and one is half the length of the other, that means SU definitely is a mid-segment.